we will prove this following. I mean, this was the last slide we had before, right? That among all network with cost function C, the largest POA is achieved in a Pigou-like network. What is C we will talk about. So, this is more general than what I said before, which was that in a linear kind of a cost function setup, the best cost we can get, the worst price of anarchy could be 4/3, right. Here that result follows from a more general treatment, okay, that you have a class of cost function, this is C. So, what that means is that whatever network you have, whatever graph you have, the cost function on any edge belongs to that family, okay. And the largest POA, price of anarchy, is achieved by a Pigou-like network, and we will say what that actually what it means, Pigou-like network. Okay. So, more formally, this is what we will show, okay, that the price of anarchy is at most this value alpha c, where alpha c looks like this, okay, and we will go over this. Like I'll try to I'll give a sketch of this proof. So, but what this is saying is, this is a value alpha c is a value that is defined for this entire class of function C. So, you have 3 supremum terms. So, you basically look at all possible cost functions from this family, okay. Supremum here means like largest value you get, and among those values of C, among those cost functions, you are looking for a value r and x, which basically tells you how to split the value across. This particular term should be remnant of the Pigou-like network. You have 2 vertex A and B. Okay, I am going to delete this. I am just going to leave what is relevant for our case. This is sort of what I mean by Pigou-like network, okay? The simplest possible thing, okay. Here the C of x is a function dependent on x, okay, the amount of flow that is coming through. This here, it is like this sort of I will say x, this is some value, let us say I don't know what notation I use later on, I will see. Okay. So, this is basically some, let us say, constant, okay, some C bar, it will be 1 most likely, but okay. So, here, so this statement, I think there was an underline. So, to draw your attention, for every set C of cost function and every selfish routing network. Okay. So, selfish routing network is a type of network we have been talking about, where people are selfishly trying to decide which is the shortest route they can take to go from A to B, okay, that class of games, such that the cost function is derived from C. The price of anarchy is some value derived from the class of function this, from a set this. What this is the selfish routing network situation you would get if you had a Pigou-like situation, okay. So, at the end of the last talk, what did I say? That no matter what network you have, the worst possible behavior is actualized by also a very simple Pigou-like network. That is what we are claiming here, okay. And that corresponding Pigou-like network looks like this, okay. So, is that correct? Is that okay? This is just a definition. You do not yet know, I do not expect you to know why this definition came about. All I am trying to say is what this actually represents, what this quantity is, just so that you can draw some connection to what you have seen before, okay. That any network, selfish routing network with cost function derived from this class C, you have a value alpha c which can be defined like this. Whatever is the value of this quantity based on that relation, the price of anarchy for this network would be at most that. So, it again tells you that the complexity of the network structure does not matter. The worst possible thing can also be seen in this most simplest possible network. The cost functions do matter. Okay? So, that is what we will see now. Okay. So, let us start. So, you have, I am going to set up this Pigou-Lite network. So, you have 0 to D, okay. O is not 0, it is O for origin and D for destination, and you have this sort of a two forked edge scenario. You have R amount of traffic, okay, starting from O. The cost function on the lower edge is C of x. So, whatever amount of x is the amount of flow that is going, this cost function C x will tell you how much delay those people will sort of experience.
Can you tell what is non-negative traffic rate? So rate.
Yeah, it's like if I send R volume of flow, right, starting from O, of which x is directed through this, the traffic experienced by each of those individuals would be Cx. That's what I mean. Okay.
So these are just numbers.
These are just numbers. That's basically what it becomes. You're just doing a numbers game. That's as if the structure of the network literally does not play a role. No matter what however complex. That's what I was saying. From a road planning perspective, it's fine because oftentimes the roads, while you want to make like design roads properly, but sometimes the city grows and roads are there, you can't remove roads, let's say, right. So, the structure is almost given to you, inherited from whatever it was. As an engineer, now all you can do is manage flow through the traffic, and basically that tells you, yes, that's fine, that's good enough, you are not facing, this is the best or the worst anybody can do. So, now try to find the best way to assign traffic, like route traffic through the roads. Okay. All right. So, now the upper is some constant CR, this value, like you take this function C, plug the value R, the total volume, whatever value you get is this. So, previously we were talking about volume of flow being 1, right. So, C of 1 was 1 and C of x being a fraction was something less than 1. So, here it is the same idea except that it is not 1, you are like R units of flow flowing through the network. Yeah, this is the setup, okay, that R units of flow is going through this thing. Okay. So, here also the situation is the same thing, that how much unit of flow to send through the top path. Again, if you in this case also for the same logic, a dominant strategy would again be for any individual would be to take this, right, sorry, sorry, yeah, the except I do not know why, it was very late when I was doing, yeah, usually, okay. So, what is the flow, what is the amount of delay, you should know, it is basically R times C of R, right, okay. Now, but what is the minimum possible travel time? Why would it be R by 2? It is not clear. It should be over there that R was 1. So, we were talking half, yes. Over here, we have this situation of, again think of it, it is a math question. Everybody is going through this, right. How much flow should I route? This is the only strategy available for this city planner on this network, move something to there. See, that is another thing that makes this analysis so easy, because if there were lots of different roads, you had to think, okay, maybe epsilon here, delta there and so on. Over here, this is the only thing you can do, just shift something and see how much the improvement is. So, you want to be able to shift, x amount of flow, right, from that lower edge, such that now the top part is basically what? Now, the bottom part you have x times Cx, this is the lower part and this is the whatever is left is going on to this, right. And over there you have, what difference does it make? This is over here you route x units of flow, you incur a cost of Cx, R minus x is left for the top edge. So, R minus x times C of R, that is the delay. X is the unit of flow you are sending through this. You have total of R, if you send x at the bottom, the rest is r minus x. So, r x incurs Cx of traffic, so delay, this incurs the constant Cr. That is what this is, and you are trying to find the value x for which this is minimized, correct? Okay. Yes.
So is it possible that CR is half, and if all the traffic goes through CX, then the time will be 1? So CR can be less than
CR can't be less than CX.
CR can't, your R is a total volume, your CR is like a constant this thing, right?
Can be
Less than 1 here does not quite make, you are saying CR will be strictly less than R.
less than equals to 1, that the time.
So,
taken-
okay, so here that is the thing. So, when we say CR here, it is, we are no longer talking about that unit 1. We are saying previously we were saying 1 unit of flow is moving, and I fractionalize, I will send half on this path and rest of the half on this. Over here we are talking about R units of flow. So, you have to say how you split R into R1 plus R2. So, that R1 goes via one path, R2 goes via one path. So, that is the thing. So, but to answer your question, see, if I am actually going to send R units of flow, the bottom edge will also incur a cost of C of R, right. That is what this is saying. It does not make sense to say that the value of C of R is somehow strictly less than R.
Maybe it is good to write that C of x is always less than C of r. Then it would be clear.
C of x, okay, that is a this thing, right. Okay, the cost function is a non-decreasing value, non-decreasing function. That this is in, I did not write it here, but yes, the cost function is a non-decreasing function, right. So, this always holds, because x is always less than equal to r for this particular part of the discussion. Okay, all right. Okay, so just keep these things in mind. I have to clear up a bit of space so that I can draw right here. Okay. So, now what should be the price of anarchy? Same thing, just apply the formula, right?
Yes.
This thing, dominant strategy thing versus divided by this infimum quantity, which then becomes supremum. Okay.
Yes.
Have I done any other adjustment? Please look carefully. It's a small technical thing, but worth mentioning.
Where do you remove the constraint that exists? Not upper bound.
Does it matter?
The answer would be the same.
Why?
Because if it is greater than r, then it would be less than this value.
Yes, if the best possible, this allows for a bigger range, right? This allows for a larger range. If the best possible outcome is within 0 to r, right? It's a non-decreasing cost function, then this will find it. And doing it this way allows me to like argue, you will see in the proof this makes the argument a little easier. That is how I am just opening up the search space, even though I know that whatever was the optimum there within the range 0 to r will still be the optimum for the larger range. Okay? So, this is like 0 to r and this is over real number, right. So, this is x being constrained here versus x being constrained all the way, right, that sort of thing. Okay. This is just for mathematical, huh?
Is it better to consider compact set instead of a half real line?
Okay, this is half real line, this one.
Yes.
Yeah, this will allow me to do, you will see the argument, because this is not the only thing that I am going to take a supremum over. It's like it's like a vector of possibilities, and over there having no constraint on x allows me to make that argument a little bit more friendly. That's it. Okay. Okay. So I just, yeah, let me just copy this over, nothing more. So now, what did we say before? We are now arguing. So I took a network, that Pigot type network, and I saw that in that the price of anarchy is this. In the Pigot like network with R volume of flow and with cost function C, right. Now, we are going to talk about the cost function C that all comes from that given class of family C. Okay. So, this is some arbitrary set of non-negative, continuous, non-decreasing cost function. It is a very generic set of properties we require, and it is very sort of common sense for a flow network, right. You do not want negative value, you want continuous, you can't have these weird jumps, right. Like if you can't have jump from 5 to like 7 where the 6 is not there. So, continuity is a standard sort of a property you would expect a flow function to have, and non-decreasing obviously. Like if the volume is larger, time should only increase, okay, maybe it can stay same, it can't reduce. Okay. So, C we can agree class of captures all reasonable flow functions, cost function that capture flow. Okay. Okay. Now, we will show that this definition alpha C when defined this way, we will argue this, okay. Alpha C defined this way actually captures the worst possible price of anarchy in any Pigou network where the cost functions are derived from this class C. Okay. Over here the cost function was fixed. I am saying I am only interested in networks which take cost function from C, right. So, price of anarchy is like worst possible bound. So, constrain, now look through all possible, look through the class of C, right, find the C, and within that find what is R, like how large, what value of R can you find me, because again it is a worst case behavior, right. For a Pigou like network of this kind, we are saying what is the worst possible cost function C you can plug here, volume of flow you can route here, and unit of flow you can split such that this value is maximum. You agree for whatever triple that actualizes this quantity, there is a corresponding Pigou network, okay. And that is going to be the worst case behavior, that will capture the worst case behavior for among all. So, all possible Pigou networks, the worst case behavior will be captured by a network which gives the worst which maximizes alpha C based on this.
Can alpha be greater than PO? Right. According to the statement
I
that
have not, yes. So, I have not actually said why is this POA. I am just saying alpha C is this.
like alpha C, it can't be bigger than PO. Right?
How?
Like
Can you see that? Why?
no, I can't see it, but that was written in the.
That is the theorem. That is what we are trying to prove, no?
But like this supreme, the one that is the inside, that is the POA, right?
What is the POA? Yes. So, that is what I am trying to say. This quantity, just see this, okay. This quantity captures the POA of a particular Pigou network, where you are routing R volumes, R unit of flow from the origin, and the cost function is this small CR. Now, I am looking at a family of Pigou networks, okay, where the cost function can be something from this class C, the volume of traffic you route can be some value R. Within this class of Pigou networks, the worst possible, the largest possible, I am saying worst, the largest possible alpha C you can define. When I say Pigou network, that is all I am talking about.
So this supremum R that we will take in the second.
Yes.
So the same R will be there for that POA condition also, right? Or like.
Okay, first just focus on this definition vis-a-vis the Pigou network. This I am saying this is one Pigou network, right, where C is fixed, R is fixed, this is R, okay. It is R volume of traffic coming through, this is the total cost, this is a Pigou network, correct. Let us index it by this is Pigo network indexed by C R X.
For this alpha C, we are changing Pigo network. Like we are seeing all the cost functions. we are
Yes,
seeing
yes.
all the
So
Rs.
this is this Pigo network. Okay. Now for any cost function C, okay, some are non-zero value here, and X, let's call it this, right? You will get a different Pigo network. Okay. So I am talking about that family of networks indexed by C R X. Okay. Actually, I do not even need this X here for the moment. I just write it as this. Okay. This is a family of Pigo networks. Each of this gives you a Pigo type thing. Every Pigo network has this sort of a corresponding instance. From within, take any such element, and that X is basically how much flow I am splitting across.
So we are saying any Pigo network possible between A and C, the maximum of that will be.
Yes, that is what I am defining alpha C to be. This is the number as of now. But I am trying to give you an intuition as to what this number means in terms of Pigo network. Okay?
So, in any Pigo network, there has to be a constant H. Like this.
Yes, that when I say Pigo like network, that is what I mean. There is that one constant load edge. Okay, no matter how much volume you set, it is going to take the exact same amount of time. And there is another variable. That is what a Pigo network is. Yes, you were saying something?
There will vary C and that because it's a family of
Yes.
functions consisting.
Yes. And the largest possible value from that family is this alpha C. Okay. So, what we are going to show is, given any graph, any selfish routing network, where the cost functions are derived from that class of family C, the price of anarchy is at most this.
This is the worst possible Pigo.
Yes, that is what it is, at most this. What is this? It is the worst possible Pigo network. That's sorry?
It's only true for Pigo like network.
What is true for only Pigo type network?
This worst case analysis.
No, that's exactly what I am trying to say. This is the definition, this is the worst case behavior, worst case price of anarchy you can see in a family of Pigo networks. The theorem is saying that no matter what class of the selfish routing network, what instance of selfish routing network you give me, as long as the cost function is derived from C, its price of anarchy cannot exceed this.
It cannot be worse than the worst Pigo network.
Yes. Okay. Okay. All right. So now this is a table that I was saying. Okay. When you have linear like this, it's 4/3. Just by doing that sort of split the value. When the cost function C, this cost function is a quadratic of this kind, where the coefficients would be positive, the coefficients are all positive. So, A is positive, B is positive. You do not say anything about C, but the problem is based on you in a flow network, if C becomes too large and A and B, it starts to tower over this and it does not happen. It would only happen when X is remaining very small and so on. So, you might as well just assume all these coefficients A, B, C, they are all positive. Okay? You do not lose anything with assuming that. So, when it is linear, it is 4/3. When it is quadratic, it is 1.6. As you raise the degree of the polynomial, it gets progressively worse. Okay?
When we talk about the big C,
Class
set
of
of family of functions, do we also include say like non-polynomial functions?
It can be anything which is of this kind. This is just saying that it already starts to get bad when you go beyond linear. Yes. Okay. So the alpha C holds for all large class of functions which are of this kind. Okay. Now, what we are saying is that for the linear case, that simple pego thing is tight and it is the worst. Okay? Bray's paradox, Bray's with the sort of a super speed highway is also attaining the worst sort of thing, right. That is what over there also the cost function was linear. Okay.
For x, say half, that would be decreasing.
Sorry?
Like half into half is 1 by 4.
Yes.
Say, but 1 by 3 into 1 by 3 is 1 by 9. So is it decreasing in that sense?
Okay. Yes. So it means that, so over there we were routing 1 unit of flow, right. Over here we are doing R first and foremost. So yes. So over here, if it is something you route half amount of this thing, take anything, half to the power whatever, p is what do you want to take, 3, p is whatever, p is 3, that is what you said, right. So what this is 1 by 8. Now if you send fewer amount of flow, right, this is, it is reasonable, right, you take lesser time. Okay, this is how you interpret. Okay, now okay, let's do, we'll work out the details. Okay. Okay, so let's take a selfish routing network of R unit of traffic between O to D. Now let P denote the set of non-empty 0D paths of G. This is there, this is the general, this is the analysis of any selfish routing network G. This is to compare with the corresponding Pegu network. Okay. You have any graph G with cost function taken from this, the corresponding Pegu network would be this, where you are using the same cost function and routing the same volume of traffic R. Okay. So that is what this is.
How would we define selfish routing network?
It is just this thing, that you have a routing network with cost function and everybody is selfishly trying, there is no coordination, like there is no, that is the thing. Okay. Okay. So I am going to talk about flow, like as you understand, traffic is flow, you may have done network flow algorithms and so on and so forth. So what is a flow through this? Your flow is basically how you split the traffic across the paths. Okay, it is no different than how you think of if you have seen max flow min cut algorithm, is the same idea. You have this much amount of flow coming through the source and then how do you split it across the network. Okay, so it is basically nothing but a vector of values where this is the curly P is basically all possible paths 0 to D. You do not care about sort of shorter paths, other paths and so on, only O to D paths. Okay, and you take what is the flow going through each path. Okay. Now of course by conservation of flow, those ideas still hold, all the flow that is passing through the paths, all of them must add up to R, because that is the amount of flow that was amount of traffic that we were routing to begin with. Okay. So that makes sense. Okay. So here for example, see one thing, multiple paths can share an edge, correct. We saw in that Bray's network using that super highway, what was happening, the last edge was getting congested, right. If people did not use that super fast highway, they would remain split across and there would be no over congestion on one edge, right. So this sort of thing can happen here as well. So this is that Bray's thing. So you have, let us say 25% amount of traffic is coming through here. Okay, it is some example of some flow. This is the rest of the traffic comes through here. Whatever comes here, a piece of it basically gets routed through this. 50% of this gets through here. So the rest of the 25% goes through here. Okay, and whatever gets collected here, which is 25% from here, 25% from here, and the rest gets routed here. Okay, so this edge is receiving flow due to multiple paths. One path is this, and the other path is this. Okay. So can you quickly tell me how much should be the, I sort of wrote down, I think it should be correct, let us see. Yeah, we already worked out O to V is O to, yeah, O to V is 75% because 25% has gone through this, So, this is the 75%, W2D again is the same thing, 50% coming through here, 25% coming through here. So, this is a 3/4 and so on and so forth. Okay. Now, can you tell me what is the shortest path? I mean, we have done this already. What is the shortest path in this sort of a flow network? Time.
The superhighway.
Tell me, what is it? The superhighway exists in this network, so you tell me what should be. You are saying it involves a superhighway, right?
This is the superhighway.
Yes, that's the one is the zero edge.
OVWD.
OVWD, yes. Why? You're saying something? You can tell. Speak louder.
So
It's fine.
you're asking for the optimal, right?
I'm talking what is actually shortest time path. Like when I say shortest path here, I mean minimum time travel.
It's because from O to V and W to D, it's only 0.75, but from O to W and V to D, it's 1.
So say that again.
O to V and W to D has 0.75 as the
Okay.
cost, but for rest of the edges, except the middle one, it's 1. So you are obviously gaining.
Yes, this is the shortest path. It's unique, right? No other path. The presence of that highway makes that the shortest path. Okay. Okay, so keep that in mind. Okay. So we just need some notations so that it makes sense. Okay. So the notations don't matter. Just try to keep a mental picture. We just agreed that an edge can be used by multiple paths. So that's all I'm doing. So I'm just aggregating the flow across that edge. I'm just summing over all possible paths, O to D paths, such that the edge E actually appears in the path, right? And then I'm just just adding up how much flow is via that going through that path, and I'm just going to add it. Okay. All right. So we define in the equilibrium flow as the traffic travels only along sort of the fastest O to D path, and we saw it, right? That's how people logically think about dominant strategy. What is my shortest time of travel no matter what it is, no matter what others are doing. The same analogous idea holds for the equilibrium path also.
These paths do not specify the number of people going on them, right? This is just path.
So this is with respect to a flow.
Not the above definition that we had, say FP, P belonging to curly P.
Yes.
So these are just paths, right? We are not considering the people.
So F considers that only. F is how much flow is going through this edge. It's equal to how much is this edge, how many paths are actually, so if F of P is 0, then it does not add anything. But all those paths along which there is some unit of flow going and the edge E appears on that path, that's what you're aggregating here. It's this example, see. This edge W to D appears in two different O to D paths. One is this path and the other one is this path. We just argued that this makes it the shortest path. But regardless of that, there is some flow here. So this edge gets used by both this path as well as this path. So the congestion, flow or congestion on this edge is due to both the paths. That's what I wrote when I said 3/4 here.
But we need to specify the number of cars going on each route.
Okay, so here all that is part of this F value. F as a flow is routing R volumes of flow. How much it is sending through the path P is captured by F of P.
Those F will be given to us. Right?
Yes, this is definition with respect to a flow F, which happens to be routing R units of traffic. Okay, so that's the thing. This is entirely based on a given flow F. Okay. All right. So now, see this. Try to understand what this is sort of I'm trying to say here. We are talking about, there can be many different ways of routing flow in this network. This network looks very arbitrary, right? It's just a graph. We don't know how it is. There might be many different ways of routing flow, but we call a particular flow to be an equilibrium flow if once you have sort of, when you see how that flow is, the traffic it induces on the network, the traffic is due to the flow only, right? When there was no flow, there was no traffic, the roads were empty. The traffic exists only as a function of that flow, right? That, so therefore, with respect to that flow f, the shortest time traveled path is what we are interested in. Is it okay? Okay. Now, so among all flows, the flows that actually sends traffic based on the cost it induces, the traffic it induces, it happens to send traffic along the shortest route is called the equilibrium flow. Yes. Okay. So, this is very analogous to that dominant strategy argument that we were doing. Okay. All right. Now, we define more precisely to be a flow to be equilibrium if whenever there is non-zero unit of flow through a path, okay, that path is the shortest minimum path, is among the short. They might not be a unique. In that example, there was a one single path, but there could be other paths because this is a general graph. That's just a Pigo network, right? That's actually Braze, but okay, right? So, this is the thing. Whenever you have non-zero unit of flow coming through a path, that path basically is the shortest possible time travel path. So, what does that mean? Don't send traffic through paths which are not the shortest time travel path. Okay? That's the equilibrium, that's like the steady state. That people have decided, okay, this is the shortest path, everybody is like, everything is moving through the shortest path. However many there are, as long as there is some unit of flow, it's always, we can see the network and say, okay, all flows are going via shortest unit path, therefore, this is an equilibrium flow. Okay? All right. So, now tell me, is this an equilibrium flow? Why?
They are using multiple paths.
Which multiple paths?
Not all
See,
paths
not
have
multiple, using multiple paths is not an issue.
not all paths have same rate, same cost.
Correct. We discussed, right, this is the shortest path. The shortest time path is the one that goes through the highway. But I am also sending traffic through here and I am sending traffic through here also. This is why this flow, right, this sort of a split of flow where 50%, 25% goes through A7, this is not an equilibrium flow. Okay? P hat is just defined, like I am using P here to define a generic path, right. P hat is some path between 0 to D in this graph, that is all. Okay. Now, I think I missed something. Okay. Okay. So, now I am going to try and think about, see, the price of anarchy requires me to say what is the time taken by the definition of price of anarchy is this. I did not formally define what it means price of anarchy. In generally what it means is what is the worst case behavior, what is the behavior in a equilibrium compared to the optimum social this thing. Okay. So, this is why I am going to talk about this entire this thing, total cost due to the flow f, total time taken due to flow f. So, that is what C of f this thing. Now, given this, what can I say is the cost for flow induced by flow f. So, I am going to use the word cost as a stand-in for total time taken, okay, because otherwise the sentence are becoming too verbose. So, now I know I have a flow f, let us say, I have this cost function on the edges. What is the reasonable definition of the cost of this path P due to the flow F. It should be just this, right? The flow F gets split across edges, right? And I just see that on this, okay, this should be E's on P. This one, sorry. Yeah, sorry. I'll fix this. Oh, yeah, okay. Yeah, sorry. Now, so I said the cost of flow, you know what I mean to say, that across the entire thing, what is the total time taken. So, naturally, I can repurpose this and get the cost of flow can be defined to be this. Flow across path P times the cost induced by this flow F on that path P, correct? And I add this and I aggregate this across all possible O to D paths. If a path is 0, this will basically contribute nothing and so on, okay?
But there may be some other flow going through the same one of the edges and inducing more cost on that, right?
But that will also be part of the same flow, no? Flow is what at any time this is the way I am routing the traffic.
Yeah. You mean like say in the fractions you say that half is going through one path and the half is going to the other path,
Yes.
but these paths intersect at somewhere.
Yes.
And then
That's what this would be taking in, right? This is what is Cp of f. It is saying this path take any path which moves from O to D. What is the cost? What is the cost due to the flow f? That's what this Cpf is saying. Okay. Now, how much flow there is on that path, the volume is given by f of p. F is the path, f of p, like we were talking about half, 1/3 and all, right? That is this value here. The cost is this is the value of flow on the path p. And I am now adding over all possible paths. Of course, some of the paths may have common edges, that is fine. But I am doing, it is like here is a network, there are all P1, P2, P3, P4, Pn different paths. I am just adding up what is the flow across, what is the cost of the flow across path 1 added with the cost of flow across path 2 and so on. This together will tell me the total flow, total cost of the flow on this network, like total delay experienced by anybody. One such term tells you the delay experienced by people who are on this path P. There are f of p of them. Each one is experiencing Cp of f amount of delay. So, together they are experiencing this much. Now, I add over all paths. So, this is the total delay across the network. Okay? All right. Now, so this is one way of capturing the total flow in the network. Is there another way?
If we are aggregating using the paths, we can also do it the normal way like we have done using just edges.
Very good. That's exactly right. Yeah. They mean exactly the same, right? The edges are additive over paths. I am adding over path. I can just exchange the summation and do the same thing. So now you understand. This is clear, right? This is clear for everybody? So think that f subscript anything is that how much of this flow f is going through this, be it an edge or be it a path. Okay. Now, okay, so we have set up some definition. I have sort of pointed you all towards something. No, f of p. No, f of e is how much of flow is going through the edge E. So, in that Braze network, that large edge, there I was routing. So, when I was sending 75% flow, right? Yes. Yeah. Right. So, the total delay is due to those things, like the volume times the cost. So, yeah, this is the part that you have to be a little bit this thing about, right? So, in normal network flow type of thing, we have this notion of capacity. Don't send me more than this amount of flow, right? Over here we don't have that bound on roads. This real world road, that sort of because nobody, practical problem, nobody is counting cars. I think Sakit was saying we can have a sensor where say no, more than 100 cars not going through this road at a time. That's much more probably difficult to this thing. So this is why, okay. So we don't have an upper cap on how much capacity, just that this is the flow, this is how much cost it will incur. So now what is left to show? So let's just try to take, we understand how the flow is spread across the paths as well as how the flow is spread across the edges, right? What is left to show then? We also saw a definition of an equilibrium flow, which I hope made some sense. Think about it a little bit, why that's a reasonable definition of equilibrium flow, why it extends, it's analogous to what we have been talking about as being the dominant strategy thing, okay. So ultimately to show, this is the result we have to show, right. So the price of anarchy of this given network is at most this alpha c. Alpha c at this point is just a number, correct. So in this network, I have to compare what is the optimum flow, let's call that f star. Optimum flow here means minimum cost flow, right, with that of an equilibrium flow, correct. The ratio of that will give me an expression for the POA. That's it. So that's what we will do, and then we will show how that is connected to that PIGO thing that we have set up, okay.
Does the equilibrium one capture the worst case dominant strategy?
Doesn't it? Because the equilibrium was saying, what does it say? That among all the flows, only those flows are equilibrium when they only route their flow across shortest time paths, right. That's what the dominant strategy I always think. I'm just thinking, oh, I'm going to take this path or that. This is at least as good as for me than the other.
And you're just calling that like equilibrium.
Yes. Okay. So you know that dominant, we talked about this terminology. There are a lot of I have absolute sympathies. It's it baffles one's mind, terminology, notation and all. It takes a bit of time getting used to, then it will become this. So dominant strategy equilibrium is one where everybody is playing a dominant strategy. So because here we are talking about selfish routing network, everybody is selfishly thinking about their thing. So everybody is playing dominant strategy, and therefore that resulting flow is the dominant strategy equilibrium flow. Okay, that's the this thing. Okay, so it's sufficient to prove that this cost of this equilibrium flow divided by the cost of the optimum flow is at most alpha c. This is the definition of the price of anarchy of this network, and this is what we have to show, this greater than at most. And yes.
So if it's an arbitrary equilibrium,
Yes, there can be multiple equilibrium flows. It's something. It's one.
not when you define definite star, I thought any cost flow should be an equilibrium flow, because in cost flow you have empty non-zero only on minimum cost.
Sanjay, there can be multiple equilibrium flow, let's say, but the price of anarchy tries to capture the worst possible behavior. So we are saying take any equilibrium flow, and I'm going to compare that to the best optimum, socially optimum outcome.
So in selfish routing only an equilibrium flow is so arbitrary equilibrium.
Yes, that's what it is. Okay, what he's saying is an interesting point, that is a mean cost flow itself an equilibrium dominant strategy flow? Is it? In the examples of PIGO network that we saw, or the Braze network, it wasn't. In the Braze network, the minimum cost flow is ignore that superhighway, but the dominant strategy flow or the equilibrium flow was always take the middle route.
It's like the difference between greedy algorithms and optimal.
Yes.
You're
Yeah.
trying to take the least, like the best for you.
Correct. So the behavior of the agents is very greedy, right? They are not coordinating with anybody or anything. If they could, they actually would realize this is not the best thing that they could do, right? But coordination in such a large situation is impossible and not possible. So, the traffic lights actually try to enforce that coordination, like without people actually communicating among each other. That is a different thing. So, that is what we try to do. Okay. But yeah, that is the point, that I do not know what others are doing, I have no control, I am just going to behave greedily. That is the equilibrium flow. We are talking word equilibrium may be confusing, but what we are talking about is dominant strategy equilibrium, that kind of equilibrium, not the best possible equilibrium. Okay? Yes.
It might be that the minimum cost flow is also in equilibrium. In that case, at POA will be 1. That is also less than alpha C.
Yes. Of course. You can have a network where you cannot do wrong. No matter how selfishly you behave, the best possible outcome is automatically attained. Yes, it is a general network. Okay. So, any idea how we can prove this? Okay. Think. So, the cost incurred by any edge is due to the flow on that edge, correct? So, you change the flow, the cost changes. That is the nature of this beast, right? Now, if a thought experiment, if I froze on any part, on any edge, I said no, like that pivot top edge, you will only incur this precise amount of cost, okay? And that cost is the cost incurred by the equilibrium flow. This shouldn't have come in together. Just focus on step 1, okay? So, we agreed that the cost due to an edge is due to the flow on it. Now, I am saying, suppose I do this thought experiment where I say on this edge, no matter what amount of flow you are sending, the cost will be incurred. The cost incurred will be the cost incurred by the equilibrium flow. Okay? Then, what can you give a description of what would be the optimum flow?
Less than FE.
Any flow. Is the question, is the point clear? On every edge, on every edge I am freezing, I am saying the cost here is going to be a precisely a particular value. That value is the cost that you get by routing the equilibrium flow. Then in this redesigned network, let us say, what is the optimum flow? The equilibrium flow itself, right? Because the equilibrium flow works with that sort of its own cost that it's inducing. If you freeze the cost, when do I get an improvement? When I move things around. I'm saying I'm freezing it, this is it. Then all other, there cannot be a better flow than this. Okay? Okay. That's the mental picture I want you to have. Okay? Let's prove this thing. This is basically saying exactly that. Cost on an edge E induced by the equilibrium flow on that edge E is this thing, right? F is the equilibrium flow, the amount of flow units going through the edge E is Fe. When I apply the cost function on this edge E, I get this CEFE. So, I have frozen this value and now I am saying what is the best possible flow I can get, right? We agree that the best should be the equilibrium flow. So, any other flow including the previously optimum flow can only be higher, right? Okay. Can you prove this a bit formally? Like, is this enough? It seems like it should be, but is it enough? In other words, that particular optimum flow, right, is it not possible that when it still somehow manages to get a, meaning it still even though it is using the cost the cost induced by the equilibrium flow, but still its distribution of values among the R units of flow that it is moving, right? It distributes it in such a way that it still gets better than this one, than the equilibrium flow. Because the equilibrium flow has a very stringent requirement. Any time you send a flow through a path, right, as long as a path has non-zero flow, it has to be the shortest path, shortest time path, a minimum cost path. But the optimum flow has no such constraint. It can route through any which way. Maybe it uses some longer distance path, moves around things a bit more carefully, reduces congestion overall, and therefore gets an advantage.
It will still have the same amount of cost.
Okay, the edges are
Yeah.
so
So because the
edges are fixed. Like, even if changing the traffic, say routing it to different one, but
It would only increase.
that will be more than
so this value is fixed.
yes.
You are saying this value is fixed. So, okay, let's see. Maybe this is. Let's say let's take out that example. The braze example should have been here, no? Yeah. Okay. Can you see from there? Firstly, we saw that that was not an equilibrium flow, the one that was routing 75% through this and 25% through this and so on.
Question regarding definition of equilibrium flow. So, equilibrium flow, if there's non-zero, if there's an edge which there's a path which has non-zero flow, then it has to be the shortest path. Should it be the shortest path among the edges which has non-zero flow, or should it be the shortest path in the whole graph regardless of the flow?
No. It is the shortest. First and foremost, we are only looking at path which go from O to D. That's one thing. Okay. Yeah. So anyways, for a general network, what we are saying is, let's look at the definition. I hope I have written it precisely. Let's both look at it together. Yes. If we have zero flow through the highway,
Then it is both the mean cost flow and an equilibrium
yes,
flow.
Yes.
That's an equilibrium.
yes,
Even though it's not the dominant strategy.
Correct. okay. So there can be multiple equilibrium flow. I am just saying that actually this is what happened, right? That this is why this flow, this is not an equilibrium flow, right? This was the example. So, but if I completely did not route anything through this, if I suppose kept on this one was 75% and I'm moving thing, would that be an equilibrium flow? So, I am sending 75% here and 25% here. Would that be equilibrium flow? Why? Why not? Some people are saying yes. Who's saying yes and who's saying no? Sanjay?
Okay, if you put 50 only, it's equilibrium because the
50 is the optimum. 50 is the optimum. But I am saying there can be other flows through the network also,
So
right?
it will be
I am sending
1.25.
75% through here and I am just ignoring this.
the costs are 1.25 and 1.75, and the mean cost path will be 1.25, but we have a non-zero flow for 1.75.
Yes. So that's why it cannot be. Okay? Alright. Okay. So I was going to say something. I forgot. Okay. So we will come back to this claim. Okay. So okay, do you understand what I am saying? So yeah, that's the intuition. It does not happen, but still we need a proof for it, a more rigorous proof, that if I add up all the flow using this cost function, but the amount of flow going through is f star e, right? This is like a sort of imaginary network where I am sending some units of flow, but the cost accrued by them is like a fixed value, okay? And that fixed value is obtained from somewhere. It is a separate this thing. It is a fixed value, and I am aggregating whatever this is. It can only be worse, the travel time wise can only be worse than whatever induced this cost. Okay?
When you are taking the equilibrium flow, so the cost that it is taking is less than any of the other paths. Right? Before fixing, say, the edges,
yeah,
the cost that it had total
yes,
was less than the other paths that were there. Right?
yes, that's the definition of equilibrium flow.
So
Correct.
then after, if we fix those edges, so then any other path that we take will be more than.
Correct. That's so. Then my next question was, where are we using the property of equilibrium? That's where we are using. Okay. So why otherwise does the other thing is to say, does this inequality hold even if f is not an equilibrium flow? Do you think it will hold if f is not an equilibrium flow, and I do the same thing, I freeze the value and so on and so forth?
So then you will be able to find a better one. So it may or may not.
What do you mean better one? Can you come with an example? That would be great. Among the things you have seen, you should be able to
Let's
come.
say the path where we were dividing them in half and half.
Okay.
So
That is the worst case equilibrium, right?
What is the worst case equilibrium? No, we are talking about an arbitrary equilibrium. We are talking about an arbitrary equilibrium flow, and we will compare it to the best optimum solution, the optimum flow. And thus the worst possible flow will also be sort of be part of that thing, right? And
taking this inequality, the edges that we have frozen are of some other f, but we are seeing for f optimal only.
what do you mean of another f? The edge belongs to the graph, right?
Yes, you are saying that instead of fe, if we have some other flow,
Okay.
and then we freeze those edges.
So I am saying, suppose I did not have this freezing the cost of every edge e at equilibrium value. If I am saying, suppose f is some feasible flow, some flow, not necessarily equilibrium flow, then also would this claim hold?
Equilibrium flow may have this. It is some
What does the equilibrium flow would have?
the value will be maybe less than that. So this won't happen.
When you say value, what does that mean? So, see, whatever flow you send through, there will be a cost induced due to the flow, cost on every individual edge. That is that value CEFE. C is the cost function on the edge E, right? And f of E is the unit of flow that f is sending through E. All that is correct, fine. I am just saying, if f is not an equilibrium flow, meaning f is a type of flow that can send units of traffic even across non-shortest path routes, then also would this claim hold?
Is it CE f dash E, but in the lower one we will still have fe in front of CE f dash E, right? Or not?
So
Inequality.
it's the same inequality except for the idea that f is a same inequality.
Only the edges of the
What is it? Okay, yeah.
You were changing it. Cost also, right? Na?
So we have
This-
f dash, right? If you are changing
Saying?
the
Wait. This hold. If not equilibrium flow. Meaning, take F to be something, a flow, which also sends Ra. So, therefore, there exists some path P, okay, so that when F sends non-zero amount of flow, but P is not part of the shortest among all the P in the class P. The edge appears in P, F E. Is this the notation? Okay.
This will not work. This one.
Try to find an example for this, where this would be. Okay, I'll talk to you later. Okay, fine. There you will see where we are using the definition of the equilibrium. It's sort of crucial. Okay. So, fine. We know that if the values were actually frozen, so let's assume this is true. Okay. If we knew that the cost was actually frozen to be whatever the equilibrium flow cost was, the equilibrium cost itself would have been optimum. Okay. Now, but that's not happening. This is just an observation, okay, as of now. Now, let's say how good is the optimum, the F star flow, optimum flow compared to the equilibrium flow F. That's what the price of anarchy captures, right? Across the network C of F by C of F star, right? But now you should be able to see that this F, the flow that is moving through the network, it's like this broken into pieces of like how much flow is going through each path and so on and so forth. The cost of the flow is basically aggregated over the paths through which the flow is moving, correct? So, the intuition is now is to show that the effect, the difference between the way F, the flow F star, the optimum flow, routes flow through every edge versus the way the equilibrium flow routes the cost incurred by the equilibrium flow on any edge versus the cost incurred by the optimum flow across any edge has that alpha C property. That's the thing. Okay? So, in a way, instead of thinking of the whole graph, think about each edge as being a network in itself. So, across each edge, if I knew that that F star is no better than F by a certain amount, then across all the edges, I would have the same bound. Okay? That's the analysis. So, okay. So, here, think about even a simplified Pigou type network. So, Pigou has this two type of thing, right. Now, I am actually just looking at one single edge and I am comparing F E versus F star E. The cost on this edge is the same for both depending on how much volume of this thing, and I am going to say depending on what F E sends, the cost incurred by this versus how much unit this F star sends across this edge has basically is no worse than that alpha C value. Okay. All right. So, now notice something, alpha C is a